Okay, so yeah, I guess Thursday night was exciting in a not necessarily good way for y'all there in New York, especially those of you that were on campus during that event. Glad everyone's safe. And I have not heard any position of the provost on how we will make up that time. So they may just leave it up to each individual professor. So I might choose a lecture and provide a recording for that, and also, just schedule a time outside of class, outside of our normal class hours, to actually have a class period. And if you can make that, that'll be great. Otherwise, we'll just expect you to watch the video. So technically, we're a little bit behind, but not to worry. We'll find a way to catch up. And as explained, I postponed the current 2 assignments, and we'll try to get caught up on those also. And each assignment I intend to be pretty easy. These are new. I did not do these MATLAB type assignments last year, so I may underestimate the amount of effort any particular one takes, but hopefully each one's fairly easy. So I know senior year's a tough year for you, and my course is as important as every other course that you have, but we'll just trying to manage your workload. But we will try to get caught up. I will be creating a exercise on the probability theory, random variables, and random processes that we'll talk about today. But I have not released that one yet. So we'll try to get caught up. So let's see. Let's look at a few things. So I did ask you all to do some polls, and I got a few responses, 9. And I'm not sure if I put a due date on this one or not. I know I put an informal one, but I'm not sure if I have a setting on it. But it looks like, you kind of understand things until we get down to autocorrelation, cross-correlation, power spectral density, and that type of thing. And that's expected. I talked to the professor that normally teaches that, and that's in line with what he said is covered. And some of these things are like this stationarity and ergodicity and that type of thing are more in line with a graduate course. But we need some of that information, so we'll put it out today. And again, enough so that you can understand the rest of the material. Likewise on Git, there was a 7 responses here. So it looks like, some of y'all have had exposure to Git, some of y'all haven't. So if you want to continue sharing, updating, submitting things via Git, I think that's great. And I will kind of continue to do a few little hints on how to do that. Maybe I'll post some references, but I will not require that. So if you want to just submit your code as is to me via Moodle, that's entirely acceptable, right? So this course really has nothing to do with Git, and it's just a tool, right? And I think it'd be great for you to learn that tool, but I don't necessarily want to take a lot of class time, and I don't want to overburden you having to use a tool that maybe you're not that familiar with. So so I think that handles that. So let's dive into the lessons for today. Let's see. There we go. So we had introduced amplitude modulation and talked about that. Let me expand that. Hopefully you can see this. So we noted that amplitude modulation in its basic form is multiplying a carrier by the modulating signal as basically a time varying coefficient of this carrier. And that gives us this modulated signal. And we noted here that we can, there we go. We noted that we can demodulate this by regenerating this local carrier and multiplying it. And we go through this math, have fun with trig identities, and find out that we've got this modulated signal here. And then we have this signal at twice the carrier frequency, which we can easily filter out, right? And this 1/2, just a scale factor, we can compensate for that by adding a power of 2 here, factor of 2, I'm sorry. And we can also look at the spectrum here. So, but the difficulty in this is that we need to replicate this frequency exactly, and also the phase exactly. And that's non-trivial to do, especially, let's say, in a mobile environment where you might have some Doppler shift. And just in terms of cheap receivers, maybe the frequency isn't as generated as precisely and accurately as in a broadcast transmitter type of situation. So, and certainly the phase is non-trivial to do. So we can do this. There are techniques to do this. Costas loop, just to toss out some terminology, but they're fairly complex. And so for broadcast type applications where we've got one transmitter that we can afford to put some extra money into, and then a whole bunch of receivers where we really like those to be cheap, right? So the way we do that is we introduce a little bit of carrier along with this modulated signal, right? So this is what we had before, the cosine omega CT times the modulated signal. But now we add in some carrier that's scaled by this factor A, this coefficient, right? So we can factor this cosine omega CT out, and we have A plus the modulating signal, right? And so we see we have a little bit of energy in the modulated signal and a little bit of energy in the carrier. And we can kind of relate those two by looking at the peak of this M of t, right? This is a function of t, so we look at the maximum that we would expect to get out of this and provide this ratio. This mu here is a modulation index. And without going into any proofs or details, we're going to claim that mu needs to be between 0 and 1. Okay, so 1 would be what we would call full modulation or 100% modulation, and that's normally the goal. We have more modulating energy in a modulating signal, and the energy in this A here is, well, it's not so much wasted because that's how we actually implement the cheaper receivers, but it doesn't add to our signal noise ratio or our the performance of our receiver in the end, right? So we like most of the energy in this MT, but if we go over 1, then we're going to have a modulation distortion type issue, and that not only distorts the signal but also broadens the bandwidth significantly, and so that would cause interference to adjacent stations. Okay, excuse me, I need to close this door here. I'm in the library again. I just realized that door was open. And so the point of all this kind of modified version of AM modulation is to end up with a very inexpensive demodulator in the receiver, right? So now demodulation is a reverse of modulation, and now we want to take that received signal and extract out the original modulating signal, right? So that may be voice, music, or data, that type of thing, right? So we can do that simply by putting in a rectifier in the form of a diode. And now we're going to only conduct when the signal is positive, right? This is the received AM signal. And so it's only going to conduct when it's positive. So when the RF signal, the modulated signal, goes negative, it's not going to conduct, right? It's going to turn off. But also, as when it does conduct, it's going to charge up this capacitor, right? And then we've also got this R resistor here in parallel with that, and that allows the capacitor here, the charge on this capacitor, or if we use our relationships from your electric circuits class in sophomore year, this is going to result in a voltage here, right? And so when the diode first conducts, it charges up that capacitor, and then that RC time constant here, will provide for that charge to hold to a degree, but drain off a little bit, and then it gets reset then on the next positive going excursion of this modulated RF signal. And then when it drops off, it starts to discharge and so on. But we need this R to drain off this charge, because if we see here, everything's kind of good. We're kind of tracing out this envelope that represents the original signal. But as our modulating signal goes down, eventually is going negative, then if our R is too large, that charge won't drain off, and we'll trace out this, regardless of what this signal's doing, where our R is limiting how fast that charge is being drained off, and therefore holding that voltage higher, right? And so we adjust this RC time constant so that it drains off the charge fast enough to be able to trace out this modulating signal. Okay, and so if we do it right, we can kind of see, yeah, it's a little bit jagged, but we can filter that out a little bit, and we'll see that we trace this envelope, which represents the modulating signal, the original modulating signal, quite well, right? And this is super cheap, right? A diode and a capacitor and a resistor, whereas before we were actually having to generate this cosine omega CT, so we need an oscillator, but more than that, we needed a circuit, a tracking loop, to be able to match these two signals up exactly. So here we don't. So this ends up being a very inexpensive demodulator. So a couple of things with AM modulation. It's susceptible to additive noise, right? So if we have the classic is like a lightning storm in the area, or that will create large amounts of noise within the spectrum that is traditionally where AM modulation is traditionally used, right? And a lot of energy there, and that is additive to the signal. And so you cannot distinguish it between this M of T here, right? It's adding to that signal, and it's going to manifest as static and pop. So we see this in lightning, auto ignition, kind of old school autos, fluorescent lighting, actually high voltage transmission lines. You drive underneath those and near those, you're going to get some static induced into your receiver by simply adding to this MFT cosine omega CT. And again, we're not going to go into the theoretical details of this, but these side lobes here, this upper sideband and lower sideband, this is space proportional to the spectrum of the modulating signal, right? So, and in this case, we have both a lower sideband and an upper sideband. And I think I noted in a earlier slide last week that we can see that this information actually redundant, right? Remember that this is this is a real signal obeying Hermitian symmetry, so that we can choose to only look at the positive frequencies and reconstruct the negative frequencies by simply taking the complex conjugate of them. Since both the negative frequencies and the positive frequencies of the modulating signal get mapped to the RF modulated signal, then that implies that these sidebands are redundant. And so what we can do is we can choose to generate only one of these sidebands. And sometimes that's the lower sideband, sometimes that's the upper sideband, and only transmit that. So there's a lot of radios, and like long range marine radios use high frequency single sideband type modulation. Amateur radios, also known as ham radio operators, will often use an LSB or a USB type transmission. So, but AM modulation has this kind of big issue with noise. So let's look at an alternative. Before we looked at modulating the coefficient, but let's look at modulating the argument of this cosine, right? And we can do that by modulating either the frequency or the phase. Actually, let me think I need a T there. So the book introduces instantaneous frequency, and that's an important concept if we're going to do a lot of analytical analysis with frequency or phase modulation. And in my original notes from last week that I uploaded to Moodle, I did not have the slide, but I decided to add it just to be kind of consistent with the book. And also, yeah, it's an important concept if we would dive a little bit deeper into frequency modulation or phase modulation. And the point here is that if we take this arbitrary signal, right? So this cosine, its argument is an angle, right? If we go back to our fundamental trigonometry, the argument of a cosine or sine or any tangent is an angle, right? And so we're allowing this angle to vary over time, right? So this is kind of our generic signal. And here the textbook authors have drawn in an arbitrary theta t, where we're plotting theta t versus t, right? So this would be the argument of our signal. Now we can look at this at a particular place, and we can write the argument as a fixed phase offset along with a fixed frequency, and over a very narrow range. Think of this in the limit as delta t goes to 0, and so where t is between this range, this can hold, and we see that this traces out a straight line with respect to t, right? That's a linear equation. So our argument of the cosine is a linear function with respect to time. and its slope is WCT, and there's an offset of theta naught. The important part is to note that, yes, it is tangent at some portion of this theta t. Now we could then, in the next instance, maybe draw a different tangent line with a different omega c, and possibly a different theta naught, and so on, and keep drawing these little tangent lines. So at each point, then, we're going to define this instantaneous frequency, right? Where this omega I is essentially the slope of the phase, the overall phase of that signal at that time, right? At time t. And so we have this instantaneous frequency, and we can also derive this theta t from that omega I by integrating from, the dawn of time until now, right? T, whatever t is, right? So we can integrate all of those things and arrive at this. So we can see that we can implement this by viewing these as instantaneous frequencies or phases also. The phase is kind of trivial because it just maps directly there if we allow this theta naught to vary with respect to time. So that brings us to angle modulation, right? So we're going to now choose to modulate this theta of t by either modulating the omega here or the theta here as a function of time, right? Looking at this instantaneous frequency at any given instance, we're modulating these two particular values, right? So when we look at this in a generic case, we call this angle modulation, and we're going to look at frequency modulation, modifying the omega part of that omega t relationship. But you can also do it with phase, and in some cases they're very related, and so you might in your transmitter choose to generate your signal or modulate your signal via phase, and then do a little bit of signal processing to okay, I think someone just joined, just heard a tone there from Google Meet. So, all right. So so you can generate in the phase modulation, then just do some little tricks to actually emit a frequency modulated signal, or vice versa if you wanted to. But normally you might generate a phase modulated signal and then have a frequency modulation as the output. So and when you do that, you're basically taking advantage of this relationship right here, right? If you generate it in phase, then you can take the derivative of it to get the frequency modulation. So let's look at this. So we still have some amplitude coefficient out here. In this case, it's fixed. So we're going to have a fixed amount of power out of this cosine, or peak of this cosine signal is going to be constant. That's important. Then we're going to do this about a central frequency of omega c, and then we're going to integrate this modulating signal with respect to a dummy variable, but up to time t, and we're going to multiply that by this coefficient that basically says how much do we want to change the frequency at a given time t based upon the amplitude, right? So this is going to produce an amplitude of signal, right? And so we're converting the amplitude of this modulating signal, the information that we're trying to transmit, by this k of f, and that's going to result in perturbing or varying the frequency of the wave that we're going to transmit. So, and so here's our relationship. We're going to look at the maximum amplitude variation and multiply it by this scale factor, this K of F, and that's going to give us our frequency deviation. So down here, the author's got a couple of graphs here where M and T is a triangular type wave, and we see that as the amplitude increases, our signal, the excursions get squeezed together, implying that it's a higher frequency, right? Our period's getting shorter, so that means our frequency is getting higher. As it goes down, it widens out, and now we have a low frequency, right? So the frequency of the transmitted signal or the modulated signal is varying according to the amplitude. We can also take the derivative of this, right? So now we'd have a positive slope here, right? And so that's indicated here. And then we'd have a negative slope, negative constant slope, and that's indicated here, and vice versa, right? So if we take the derivative of this, we get this square wave. And so now we could modulate this as a phase modulated signal and end up with this type of signal, right? So now, one thing to note, again, we're going to emphasize digital communications, and a lot of these concepts will come back to us. We'll look at frequency shift keying in a digital system, and we'll look at phase modulation in a digital system. But there's a few things to note, even though we're going to kind of wash over the analog portion of this. It is non-linear in contrast to amplitude modulation, which is linear, right? And that's because in the angle modulation case, our modulating signal is inside the cosine function, right? So if you take this signal here, right? So if this could be our modulating signal, right? But we're pushing that through a cosine, which is a nonlinear function, right? Whereas if we were modulating the coefficient of this, like an AM modulation, well, that would be a linear relationship, right? We're just mapping that M of T onto this coefficient here, right? So the envelope is constant amplitude, right? So here this amplitude is constant, unlike in the AM modulation case, we see this type of envelope for the modulated signal. As it turns out, without going into a lot of detail, from a circuit's point of view, this is much easier to amplify efficiently. So what that means is we have to supply a certain amount of energy or power to a transmitter, and we want a lot of power out, right? But we never get 100% of that energy out. And with AM modulation, we might be struggling to get 25% efficiency out of our transmitted waveform power versus the amount of energy that we're supplying to that transmitter from the electrical grid, right? In the case of, and if you've studied this, it's because you need to preserve that envelope as you transmit it, and that means that transmitter, that amplifier needs to be linear. So you're looking at more like a class A amplifier. If you haven't studied amplifier circuits, power amplifier circuits, you don't need to worry about this, but it's beyond the scope of this course. But the advantage here is that this is a constant envelope, and so we can use nonlinear techniques and to amplify. And there's just a general rule that it is easier to build a highly efficient nonlinear amplifier than it is a linear amplifier. And so since we don't have to amplify this using linear techniques, because and I know I'm just tossing a lot of this information out there without proofs or anything like that, because the concept's important to this course, but the hows and whys are more in a circuits or implementation type of course. So that's an important issue. We can create a strong output signal with finite energy in, right? Which is important if you're broadcasting megawatts of energy and your electric bills big, right? Or your and also the equipment gets more expensive when you need to do that, right? So, but also if you're battery powered, right? So it's why a lot of analog type of handheld radios use FM modulation instead of AM modulation, right? When it's analog. Nowadays, a lot it's digital, of course. So, all right. Another consequence is that the FM spectrum has technically an infinite number of sidebands that maybe these first are spaced according to the frequency of our input signal combined with the amplitude, right? And because we're modulating that amplitude into a frequency deviation, but then because of the nonlinear aspects of it, we're actually going to have an infinite series of sidebands. So this is in a spectrum display here. This is kind of a waterfall display. You don't need to worry about that, but this is the frequency spectrum. Now, to do this full analysis, you would use Bessel functions and maybe apply Carson's rule and that type of thing. So, but generally, only the first few are significant, and the rest, even though technically there's some finite energy out to plus or minus infinity here, it quickly becomes very small, right? So, but there is some limitations on how much we can modulate or how big that KF can be based upon our spectrum considerations. So some important takeaways here is that this is not susceptible to noise in the amplitude domain. Remember, we talked about AM being susceptible to static from lightning strikes and from just thermal noise and from other noises, the high voltage lines, fluorescent lights, blah, 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 right? So that's a big problem for FM, but not really for AM. It's a big problem for AM, but not for FM because the amplitude of our modulating signal really doesn't matter in our demodulation process. So, and ultimately, that's why you have a lot of music stations will migrated from AM to FM back in the 60s or so as FM radio really started to take off in the 60s and early 70s because there's just so much higher fidelity. So again, without going into the analysis, the performance for AM gradually decays due to noise as distance from TX, from the transmitter increases, right? So if you're taking a drive and you're heading away from New York City, the farther you get, your AM signal is going to get noisier and noisier, and it's going to be harder and harder to hear. Eventually, maybe some other stations will start to interfere with it, but if there was no other stations and you're only listening to that station, it would just kind of gradually degrade, and you would have just more and more noise until you really couldn't understand what was being said. In contrast, the performance for FM stays relatively constant until it falls off rapidly at a threshold. So as you drive away from the broadcast transmitter, then your FM signal is going to still sound pretty good, right? And then kind of very rapidly, it will become very unintelligible. Again, in a practical situation, there might be another station that's on that same frequency in maybe Buffalo, New York or something, just as arbitrary. And so you might start to actually hear that station instead of the New York City one. But if there was no other stations, it would still get to a point where all of a sudden, relatively suddenly, it would go from sounding great to sounding horrible. So, and basically, if we were going to focus on analog modulation, then you can certainly derive all these relationships for the bandwidth and performance versus what we call the signal to noise ratio, where we have the amount of signal power divided by the amount of noise power. All right, so I think I'll go through these real quickly since we are behind. FM modulation, you can generate either indirect or direct methods. A direct method might use a varactor or a diode which looks like a capacitor, where you're changing that depletion region, and that's sensitive to the voltage that you apply on it. So it's got a terminal that you can apply a voltage, so you can run your signal in there, and your modulating signal, and then that changes capacitance. That capacitance can be included in an oscillator, which now varies the frequency of that oscillator according to the voltage applied on that varactor. Right, so that would be an example of a direct method. There's also indirect methods. Your book goes into a fair amount of detail on indirect methods. But again, we're going to move on from this. Reception, the turning back from frequency variations to amplitude variations is done in a circuit commonly called a discriminator. Again, we're going to move on from that. Just for fun, you may recognize this tower over in the Jersey side, just across the Hudson River in Alpine, New Jersey, and just a little bit north of the George Washington Bridge, and huge tower. And that is where in the 1930s, Edwin Armstrong invented and developed FM broadcast technology. So there's a little museum at the bottom of that that you could go to. Sorry, we can't do a field trip in this course. So takeaways, we will continually return to that nonlinear mixing concept that I introduced in the original first few slides of this original lecture from last week. We won't worry too much about the math involved, but just the concept, right? And we'll just take it as a given that we can translate these signals and in terms of frequencies and by injecting a carrier. Not many analog systems are being designed today. I've said that a bunch of times, but I hope that you can take away some of these high-level concepts and terminology. And we will now turn our focus to digital communications. All right, so as we do that, let's see. Let me now switch to our random variables. Okay, and hopefully you're seeing that. And all right, so we'll talk about random variables, probability density functions, moments. So this is like mean and variance, dealing with two or more random variables, and then we'll get into random processes, stationarity and ergodicity. And these last few we'll just accept and not go into a ton of depth because these are more for, again, a graduate level course on this, but it's some of the analysis we do relies upon our signals being stationary, at least in some sense, what we'll call white sense stationary, and that they obey this property of ergodicity. So it's helpful to at least know that these things exist. In engineering, I used to teach capstone and that type of thing, and I emphasize a lot that it's important to understand some of the simplifications or assumptions that you make when you are analyzing or designing a system, and some of those, our most common one that we assume is it's linear and time invariant, that LTI. You probably remember that from back sophomore or junior year. When you looked at Fourier transforms, you made an assumption that the signal was analytic, I think is the right term. So, and then you had to make some adjustments when it's periodic and things like that, right? So there's lots of assumptions. If you do microwave circuits, you'll make a lumped element assumption, or you'll have to relax that assumption. So white sense stationarity and ergodicity are assumptions that we will make. And it's just important to know that there is an assumption, and that there are cases that don't satisfy those assumptions. All right, so we probably won't get to these later things today. We're behind just because that's the way the courses work, but also regardless of our missed session on Friday. All right, random variable. So this first part should be a review, and but yeah, it's good to review. So what is a random variable? A variable that denotes the numerical outcome of a random experiment or process. So the classic canonical systems that we look at are a coin toss or a roll of the dice, right? So in a coin toss, we'll have a sample space, which we denote with this capital omega, which includes all the possible outcomes. So coin toss, that sample space would be the event heads, or the event tails, right? Whichever one is facing upwards after the coin has landed, whatever. That is the complete sample space. There's only two events if we assume that the coin does not land exactly on its edge. In the case of a six-sided die that we're most familiar with, then our sample space, omega, would include 1, 2, 3, 4, 5, and 6. Again, we're assuming that there's no way for it to land on its corner. That's an unstable, from a physical standpoint, it's an unstable point. So it's going to land on one of those, with one of those faces facing upwards and corresponding to one of those events. So kind of beating that to death may seem obvious, but it's important to note that the sample space omega includes all the possible events, right? And so now we map these to a measurable space, which we'll denote with this kind of funny capital E, using numerical values. For a dice, that's easy. Count the number of dots on the dice and use that as your measure. For heads, for a coin toss, we could assign a 1 to a head, or a 0 and a 0 to a head tail. I'm sorry, or vice versa, right? Doesn't matter, but we're mapping heads to a numerical value and tails to a numerical value. And then we can use our normal math to analyze everything, right? But understanding that the sample space is really heads or tails, or 1 dot, 2 dots, 3 dots, blah, 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 right? So we denote our random variables as X and Y. When they take on a particular value, then we might use lowercase, right? So if it is countable, right, then that's discrete, right? So the examples I just gave you are countable, right? You can count the number of different events in that full sample space. In that case, then we can just, these can be described by a probability mass function that assigns a probability to each of the values in E, this capital E, right? So the probability that this random variable X takes on a value A, right? So that is a discrete system. Now, we can also, at the other extreme, have an uncountably infinite, over an interval at least, that then X is a continuous random variable, right? So If it's a random voltage, then that voltage could be 1 millivolt or 1.001 millivolt or 1.0000001 millivolt. You can't really count up the number of different states or values that random variable can take within that interval. You can keep dividing that more and more, right? So it's uncountably infinite over an interval. And so then we're talking continuous random variables. So when we deal with some data sources, these are sometimes discrete, right? But if we're dealing with, let's say, a noise voltage, then it's likely going to be a continuous random variable. In this case, our distribution can be described by a probability density function, or that PDF. Now, you're probably familiar with that, right? You probably looked at PDFs quite extensively last year. This describes a probability that X lies between a range, right? Not that it takes on a particular value, because you can keep splitting this A from 1 millivolt to 1.001 millivolts or 0.999 millivolts and so on, right? So we look at this probability that X lies within this range. And you may recall that the probability that X actually takes a particular value is 0, right? It approaches 0 in the limit as A approaches B, or as A and B come together, right? So the probability distribution function, okay, not the density, but the distribution function, describes that the probability X is less than some value A within its support range. So, all right, so let's think about distribution. So the random variable describes some underlying process. These processes often follow one of a small set of well-known distributions, right? So this underlying process could be some physical process that is due to, let's say, thermal noise in a system that causes motion of atoms and electrons and whatnot, right? So, but we can model these processes using some well-known distributions. Can you name some? Does anyone want to give that a shot? Anyone want to speak up and name some well-known probability density functions that you've looked at before? No one wants to take a guess. So what do we call the process that follows the bell curve? Does anyone remember the central limit theorem? What do those?
Go ahead, Prince. You go.
Say again. Yeah. Unfortunately, I cannot understand you. So, okay. All right, we'll go back to the presentation. As happens, last year the audio was pretty poor from the room. So yeah, we have the uniform distribution where within a particular range we're equal probable, right? So anywhere in between, let's say 0 and 360 degrees, our phase could be equal probable that it's 30 degrees or 45 degrees or 46 degrees or whatever, right? So phase often follows a uniform distribution. The bell curve or the normal curve is this Gaussian, right? And if you recall, I mentioned the central limit theorem. If you combine a whole bunch of different processes, even if they're uniform or some other crazy type distribution, then they will eventually look Gaussian when you kind of sum them all together in a system of these things. We won't go into much more detail than that, but Poisson distribution is basically a discretized version of Gaussian. Rayleigh is one-sided. There's a bunch more: exponential, Bernoulli, chi-squared. These are all have some importance in communication systems. All right, so let's look, for example, at a uniform distribution. And here, this would be our PDF, or our density function. And so our probability where x, our random variable x, our particular instance of it, is lying between A and B, then the probability of that happening is 1 over B minus A. Right? Whereas for if it's outside of that range, probability is 0. Right? So this is describing the probability that your particular value, an instance of the random variable, lies between two different areas. It's a constant, right? B and A are limits, right? And these are constants. So we can look also at the distribution function. And again, the probability of x being taken on a value less than A, well, that's going to be 0, right? And but the probability of x lying between A and B is going to be x minus A over B minus A, right? So these are x is a variable here, right? And A and B are both constants defined by this particular uniform distribution, right? And but the probability of x greater than B, again, this is it's a little bit awkward looking at this f of x. At least in my mind, it's a little bit awkward, right? So when x is greater than B, what's the probability that x is less than that particular value, right? So that's what f of x is actually saying, right? If we go back to here, this probability that x is less than a particular value. So it just looks a little bit strange. You can kind of wrestle your way through, but this is the important part right here. So it has support. X is supported over the range A to B. Support means it takes on a non-zero value, right? So what kind of processes might follow this distribution? Well, I mentioned that earlier. Phase, the phase angle of, let's say, a received signal will typically follow this uniform distribution in the generic case, not saying every case, but oftentimes phase can take on any value between 0 and 360 degrees, or minus 180 to plus 180 degrees, or 0 to 2 pi, however you want to dimension it. Right, so then we can look at Gaussian distribution, and we will parameterize this in terms of the mean and the variance. Now we'll look at how we define mean and variance in a few minutes, but this is like shorthand, right? So this is the normal distribution's always going to follow this general form, but the parameters of this to give us a particular distribution, you would fill in the values for mu and sigma, which is just the square root of sigma squared. Sometimes you'll see this equation written with sigma squared, so we just move things around, move that in underneath the radical, and then this out of this quantity squared. So so hopefully this looks familiar, right? So your random variable shows up in this exponent of this exponential function, right? And then on the occasions that you look at the distribution function, then you're using this ERF function, and that comes from those conversions between f of x and capital F of x that we showed earlier. Or maybe I show here momentarily, I can't remember. Sorry. So here the support is over the whole real number system, right? So the domain of this ranges from minus infinity to plus infinity, and they can take on real numbers. So what kind of processes might follow this distribution? Well, the most common one that we will look at in this course is thermal noise, thermally generated noise. And that because actually through the central limit theorem will always follow this Gaussian distribution. So here's the conversions I was mentioning earlier. So if you wanted to derive this f of x from this equation here, you would integrate from minus infinity to x using a dummy variable. U could be anything, but it's a dummy variable, right? So, and then to convert from a distribution to a density function, you would just take the derivative of this. So, right? So you really only need one, and you work with whatever one is more convenient to your mathematics that you're doing. And we will often be working with the f of x here, the PDF, the lowercase f of x, the density function. So, all right, some axioms and consequences. When I looked at the survey results, you all kind of said that you didn't recall that well the axioms, and maybe it's just because they're kind of obvious. We state them. They're kind of the foundation that underpins everything else we do, but then we rarely go back and visit them. But it's helpful to understand these things because they are important concepts, right? So the probability of any given event happening in this random variable selection process is going to be 0 or greater. Right? It can't be negative. There's no meaning for a negative probability, right? So it's always going to be a positive value. The probability that the event is in the sample space is equal to 1, right? So your sample space includes all event possibilities. So therefore, the probability that your event is within the sample space is 1. It has to be, right? Or our sample space was not correctly defined to begin with, right? And we get a little more complex here. If we draw 2 events out of this sample space, okay, so we roll the dice twice, let's say, right? And now, what is the probability that we'll roll a 1 or a 2, right? Either one of those type events would be the probability of rolling a 1 plus the probability of rolling a 2, right? So the probability of any single value in a roll of a 6-sided dice is 1/6, right? And so the probability that we would roll either a 1 or a 2 would be 1/6 plus 1/6 or 2/6 or 1/3, right? Now that's assuming that there's no intersection of these 2 events, right? So here I've kind of defined an event to be a single roll of the dice and the results of it, right? So I'm not a gambler, but let's say you're playing craps, right? And there you're rolling the dice at least twice, right? So you roll it once and you try to match that roll. And if you roll a 7 or 11, it might be a good thing, it might be a bad thing, depending upon what roll you're on, right? So, and you win, under certain conditions, but it takes 2 rolls of dice. In that case, now our events are more complex, and then one event might depend upon the other, right? And so here we're assuming that they don't, right? So this 0 with the slash through it is the null set. So the null would be an event that is not in that sample space, right? So, or this probability is 0, right? So monoticity. So if A is a subset of B, right, then the probability of A happening is less than or equal to the probability of B occurring, right? So here, A might be the event 1, whereas in a roll of a dice, where B might be the event that 1 or 2 was rolled, right? It might be the kind of combination of this, right? So then A would be a subset of B. And so we just calculated the probability of B in that case would be 1/3, whereas the probability of A rolling a particular value of 1 or 2 would be 1/6, right? So this means that the monoticity, that the probability of A cannot be greater than the probability of B, as A is a subset or equal to B. The probability of the null set is 0, right? That kind of goes back to the definition of our sample space. So the probability that we would draw a something that is not in the sample space is 0, right? An example would be probability of 7, right? Of rolling a 7, that would be 0. Now the probability of an event being in a sample space minus some events or subset of events A, right, is equal to 1 minus the probability of A. Right? So this A could be simple as rolling a 1. So then this would be the probability of if we just looked at the probability of omega up here, this would be probability of rolling 1, 2, 3, 4, 5, or 6, right? And if we subtract out the event 1, then we're really looking at the probability of rolling a 2, 3, 4, 5, or 6, right? And so that's a probability of 1, which would be, arrived from this, minus the probability of A. In this case, A being rolling a 1. So that would be 1 minus 1/6, or the probability of rolling something other than a 1 would be 5/6. 1 minus 1/6, or 5/6. Right? So A here could take on other type of values, but that's the notion that your total sample set minus some subset of that is going to follow this relationship here. Then if we generalize this line up here, hopefully you can see my cursor. I could, and I'm not sure how on the Mac to here we can do a laser pointer. So if we generalize this statement up here, then we can have this relationship here, where now our probability of this union is equal to probability of the individual event, the sum of those, minus the probability that the event that actually happens with some overlap of E sub I and E sub J. Right? So let's think of an example, again, using the roll of the dice. E sub I could be you're rolling either a 1 or a 2. Right? So the probability of that would be 2/6, or 1/3. Right? And then EJ could be the events, the event that you roll either a 2 or a 3, right? And so that again would be 1/3, right? So you'd have 1/3 plus 1/3. This would be the probability of rolling a 1 or a 2. This would be a probability of rolling a 2 or a 3. But note that there's some intersection between these two, right? The probability that you would roll a 2, which is 1/6, 6, right? So the overlap in these, or the intersection of these two events, would be the event that you rolled a 2, right? So you would need to take this 1/3 plus 1/3, that's 2/3, or 4/6 minus 1/6. So that would be 3/6 or 1/2. Did I do the math right? I hope so, because this is recorded. But so the point is that you need to modify this result where you're simply summing the probability of these individual events by the overlap of the two events, the probability of the overlap of those two events. All right, so checking on time here. Got a little bit of time. Statistics and moments, right? So you've worked with the expected value or mean, right? So, way back in maybe middle school, or I don't know when you learn this, right? So you calculate the mean, the mode, the median, and that type of thing, right? So as we get into this level of math, now we can understand the kind of foundations of those instead of following just a plug and chug type of rule, right? So here we can have the expected value, and the way we find that, so we denote that either with the lowercase random variable with a bar on top, but more generally we have the expected value of x, and we find that by taking our probability density function, the PDF, and integrating that with respect to a dummy variable while multiplying it by that dummy variable, right? So we've got, we're not just integrating from minus infinity to infinity of f of x. Well, if you think about it, that would be 1, right? That's another little, maybe not an axiom, but something that you might have derived when you studied PDFs originally, that if you integrate from minus infinity to infinity, then you are basically looking at any value within that whole sample set. And we just learned or recalled that the probability of the event being in the sample set is 1, right? So, but that all changes when we're multiplying it by this dummy variable. So what we're really doing here is we're taking this dummy variable, which ultimately reflects into x here, and we're weighting it by the probability density function, whatever value this takes on, right? So this alpha here, this dummy variable, is going to take on a value between minus infinity and infinity, but as we integrate that, its values are going to be weighted by the corresponding value of the probability density function at that dummy variable location, right? All throughout minus infinity to infinity. We sum all those up and we get an expected value, right? So that's the foundation of the expected value. That applies for discrete, for continuous, I'm sorry. If we're discrete, then we replace the integral with the summation, and these continuous values with this probability mass function, which takes on discrete values, and also. All right, so let's look at the mean of a uniform distribution, right? That one's fairly simple, right? So our uniform distribution outside or less than A is going to be that probability is 0, right? So the value of this function is 0. 0 times anything 0, summing 0 is 0. So same thing for B. Anything greater than B, we don't have to worry about up to positive infinity because it's all going to be 0, right? So really the only non-zero part of this whole equation here from minus infinity to plus infinity, the only non-zero part lies between A and B, right? So that's where we're going to focus on, right? So we take that PDF, 1 over B minus A, and that's from the definition, and we multiply that by this dummy variable alpha and integrate, and so we can do that by hand, right? So we can expand this and do it analytically, right? So if we integrate this is a constant, right? So we integrate alpha d alpha, that gives us a squared divided by 2, and evaluate from B to A. We plug and chug here. Again, these are constant coefficients, and we just plug this into a alpha squared, and we can factor this as b plus a times b minus a, right? And we just gather the two here under this product term and the b minus a under this product term. We note that these two cancel out. So our expected value is b plus a divided by 2, or basically the midpoint. We look at this as a range A to B, and we go right in between. That makes sense, right? I hope it makes sense that the expected value of this uniform distribution, which has a constant probability between A and B, the expected value of that is going to be halfway in between, right? B plus A divided by 2. All right, so now let's quit this and let me look real quick at our assignments. Do I not have? Okay. Octave is weird. It doesn't show up as a screen because it's based on Linux or Unix or whatever. So this is the assignment that you're turning in tonight, and this assignment here is this AM modulation. I removed the need to do the FM modulation, and so here you're going to again set up some constants, and now actually those frequencies are, oh no, that's right, this is the AM version, right? So we've got 1010 kilohertz, we've got 5 megahertz signal. Let's keep those amplitudes the same as the carrier versus the amplitude. Let's do some create the time base, and then we create our carrier. This we're just going to leave as an amplitude of 1 right now. Now we're going to create our baseband signal here, and now we're simply using the same T, same sampling in time, but now we're using 5 kilohertz and then some amplitude there. And so now we can stick in our baseband signal here and our carrier amplitude here, and then multiply that. Note that in MATLAB we're doing a dot star here, means element by element instead of some matrix or vector type multiplication. And then we plot the results. So let me show you what that looks like, right? So there we have the modulating signal, and then we have 100% modulated amplitude signal. Okay, so you should end up with something like that. Now I don't have MATLAB on my Mac here, and so I'm using Octave, which is kind of a replacement of that, but you can, and I haven't gotten the communications package to install on my Mac correctly, but the last part of this is asking you to use this built-in function, right, or MATLAB, and that's the AM mod, and that's in this communications toolbox, right? And note that there's a few different versions of this. Here, this one performs transmitted carrier modulation instead of suppressed carrier modulation, where car amp, that last term there, is the carrier amplitude of the modulating signal, right? So if we look at this, you know, I say, you know, modulate this, and then, you know, compare that with an AM mod command and plot the results, and then are the results the same? So you should just plug that in. There's another term here, the any phase. You can set that to 0. That's the initial phase, and that doesn't really matter. But we've got the X modulating signal, the frequency of a carrier, and the sampling frequency. So hopefully you can plug and chug on all those things. That's not due yet, but you can get started on that as you've, I know a bunch of you have finished and already submitted the initial assignment, and so this is the next assignment. We'll touch base again on Friday on this. So have a great week, and that's it.